శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning, students. In the last class we have observed that the response of low pass filter. Our fourth chapter we are going to discuss about the response of low pass filter we have observed in the last class. So according to their response, there are four types of filters we have discussed. So in which we have completed the low pass filter, which allows the signals having low frequencies and which rejects all other frequencies. So here you can see the pass band is going to lie between 0 and FH, and the stop band is going to lie above FH. We have observed the response of low pass RC circuit using single low pass RC circuit, and also we have observed the response using second order low pass RC circuit. So in the first order, the transfer function obtained is 1 by root of 1 plus omega by omega naught, where this omega is the frequency of the input signal which we are given, and omega naught is the frequency of the signal. Omega naught is the frequency of frequency of RC, which we are going to introduce. That is which decides the cutoff frequency, that is FH of a low pass filter. So this is how we have observed the response of low pass filter. Here you can see that omega C is equal to 1 by CR, and this is the response what we have observed. So it allows the low frequency signals, that is around from 100 Hz to FC, up to FC it will allow. That is, so we have made the frequency scale which is multiple of FC. So 0.01% of FC to FC it will allow, and beyond that FC it will not be allowing the signal to pass through it. So this is the pass band. Only in this band it allows the signal. So as this is a low pass filter of passive network, what we are discussing now, because of that the gain will be 0 dB, because for a passive network the maximum gain will be 1. So if you take the logarithmic value, so then the maximum gain will be 0 dB. Maximum gain will be 0 dB. So we are going to consider the 3 dB frequency for this. That means 3 dB below the maximum value. We can see here at this point it has coincide my characteristics curve, which is shown in the black line. So where it coincides, from there I am going to draw a vertical line. So that vertical line is going to coincide with the frequency axis on frequency axis on x-axis. So that frequency we are going to take it as the cutoff frequency of a low pass filter. We can determine the cutoff frequency using the characteristics like this by plotting the characteristics on a logarithmic graph, and we can be able to know the cutoff frequency, that is the frequency, that is the pass band frequency of a low pass filter. So this we have observed in the last class. So also we have observed the response of low pass filter of second order low pass filter. So here we are having two RC networks. So if we observe here, the omega naught is going to depend upon two values, that is RC values, two RC values. So here this R and this R and this C and this C. So here, because of introducing this, so we can observe the transfer function also. So which is equal to omega naught square divided by s square plus s3 omega naught plus omega naught square. So from this equation, so what is the change we have observed is in the characteristics curve. Here you can observe in during a stop band, the attenuation of the signal is around minus 20 dB per decade in case of the first order low pass filter. So attenuation is low. So we are going to increase the attenuation. So that is minus 40 dB per decade in case of second order low pass filter. So the actual response will be like this, but practically we are getting the response which has shown in a black line here in this graph. So we are going to reduce this curve, that is attenuation. We are going to bring this attenuation line towards FC. So this can be done by considering number of RC networks. If we consider number of RC networks, then this line will be coming nearer to this EFC. So then we can say that the practical response is approximately equal to the ideal response of the filter. For that reason, we are going to consider higher order filters. So that is about the low pass filter. And now we are going to see the response of high pass filter. So high pass filter, the name itself indicates that it only allows the high frequency signals through it and rejects all other signals. So here we have to observe that from which frequency component it is allowing the signals. That means from which it is going to consider a threshold value, that is a value, a frequency value. So such that the frequencies above that frequency, selected frequency value, can be allowed by this high pass filter, and the frequency allowed by that selected frequency below the selected frequency will not be allowed by this low pass filter. Such frequency we are calling it as FL. So FL is the frequency. So FL is the frequency. So above the frequencies above this FL will be allowed by this high pass filter, and the frequencies below this FL will not be allowed by this high pass filter. So we are calling the frequencies that is the response. In case of response, we are calling this as a stop band and this as a pass band. So this is the ideal response of the filter. So if you observe, on x-axis we are taking a frequency, on y-axis we are going to take a gain. So the gain will be around 1. We can say that the gain is 1 means the output is equal to the input. So there is no loss of the signal in case of ideal, if you consider an ideal components. So in such a way, it is going to produce all the frequency components above FL at the output of the circuit, whereas it is going to stop all the frequency components below FL at the output of that circuit, high pass circuit. So this is the ideal response. And coming to the practical response, so whereas practically the response of the response will be not as similar to the ideal response. So you can see here that is not nothing but the steep will be not a vertical line. So here instead of a vertical, it will be a, a rising line. You can see here that is a blue color line. So this is the response of high pass filter. So attenuation in the stop band is around minus 20 dB per decade. So as we are considering here the first order low pass filter, the attenuation will be minus 20 dB per decade. And in this section, this is a stop band section. In this section, it is not allowing the signal to flow through it. And in this section, this is this blue color section, you can call it as a pass band. And in this section, it allows the signals that is to flow through that circuit. So hence it is going to allow only the frequencies above the cutoff frequency. Then we can say that this circuit is going to act as a high pass filter. So it is allowing the higher frequencies above the cutoff frequency and rejecting all other low frequency signals, all other low frequency signals that is below cutoff frequency, that is below cutoff frequency. So coming to the response of this RC circuit, here we are using the RC circuit R and C. You can see that we are considering here the output across the resistor, and we are giving input to the capacitor. So V in is applied to the capacitor and V out is taken across the resistor. So we can write the equation V naught is equal to V in into V naught is equal to V in into R divided by total R plus 1 by SC. So if you bring that V in to the left hand side, then it becomes V naught by Vs, sorry, V naught by Vi is equal to R by R plus 1 by SC. So this is how the equation is obtained. And then by solving this equation, so we are taking a, we are going to multiply with S. We are going to multiply with S on numerator as well as a denominator. Then we have this equation, you can see. So S by S plus 1 by CR, S by S plus 1 by CR. Then this is equal to S by S plus. So we are going to write 1 by CR is equal to omega naught. So here it is mentioned here, that is omega naught is equal to 1 by CR. So in the place of 1 by CR, we are going to write omega naught. So S by S plus omega naught, we are going to get S by S plus omega naught. So finally, the transfer function h of j omega is equal to j omega divided by j omega plus omega naught. So in the place of s, we are going to replace, we know that the s is equal to j omega. So in the place of s, we are going to replace it with j omega. So j omega by j omega plus omega naught. So 1 by 1 minus, we can write this equation as 1 by 1 minus j into omega naught by omega. Okay. Next, h of j omega, this can be obtained by bringing this j omega to denominator side. So that is, we can bring it by dividing j with j omega on both sides. That is on numerator, dividing on the numerator with j omega, and also dividing with j omega in the denominator. We are going to get this equation. So j omega by j omega will become 1, and this j omega by j omega will become 1, whereas plus omega naught by j omega will plus omega naught by j omega will we are going to get. So we are bringing this j to the numerator section. When we are bringing this j, which is in the denominator section, into the numerator section, that will be becoming minus. So then we are going to obtain the minus here, minus symbol here. That is how we have obtained the minus symbol here. 1 minus j into omega naught by omega. So if you observe the magnitude of the transfer function, so it will be given by 1 by square root of 1 plus omega naught by omega whole square. So here we are going to consider only magnitude. So hence 1 plus omega naught by omega, where omega naught will be decided by the RC components which we are using in the circuit, and omega will be the frequency, input signal frequency, which we are giving to the high pass RC circuit. So if we consider the gain in decibels, so the transfer function in decibels, that is equal to 20 log of this section we are going to write. And then if we observe here the magnitude of the transfer function, when omega naught is equal, sorry, so this is the input signal frequency, input signal, that is omega. If omega is equal to 0, then what happens? H of j omega is equal to infinity. So if omega is equal to 0, in place of omega we are placing 0. So anything by 0 will become infinity. So 1 plus infinity, sorry, so 1 by infinity we are going to getting. So then the value will be minus infinity. So when we are going to place this omega is equal to 0, then it becomes minus infinity. And when omega is equal to infinity, when omega is very high, then the transfer function will be 1. That is, if the transfer function is 1, in decibels it will be 0. So when omega is equal to omega c, that is, if both are equal, then this by this become 1. 1 plus 1 become root 2. So 1 by root 2. So 1 by root 2 is nothing but value is 0.707. That is minus 3 dB. When omega is equal to omega naught. When omega is equal to omega naught, then this will be at minus 3 dB. And omega is equal to 0, it is minus infinity. And omega is equal to infinity, it is 0 dB. So as we have observed here, so omega is equal to 0. When omega is equal to 0, so what happens? It is minus infinity transfer function. So the gain will be minus infinity. In this side, the gain will be there. And when omega is equal to infinity, that is 0 dB. You can observe here, omega is equal to infinity means at higher frequencies. So the curve, the black color curve you can observe here, that is lying on the 0 dB line. And when omega is equal to omega naught, then it is at fc. So this is the point when omega is equal to omega naught, that is a 3 dB below the, that is 3 dB below the maximum line, point 1 by root 2, which is nothing but 0.707 of the maximum value, that is 0 dB, that is minus 3 dB, 0 dB minus 3 dB, which we are going to get minus 3 dB. So this is the cutoff frequency, and this cutoff frequency is decided by the RC networks. So this is the response of first order high pass filter, and which the attenuation is around 20 dB per decade, and the gain is at 0 dB. You can see the maximum gain is at 0 dB, as this high pass filter is made up of uh, all passive components. So when the gain will not be improved by these passive components, so hence the output is equal to input. So we are going to obtain the gain as 0 dB at the highest frequencies. And when we are going to observe about the second order high pass filter, so if you observe the second order high pass filter, so we are going to consider the two RC circuits, that is RC, and we are going to connect another RC circuits in cascade with the first RC circuit. So the transfer function is going to become h of s is equal to s square by s square plus s3 omega naught plus omega naught square. So this is what transfer function we have obtained. Here omega naught will be decided by the R and C components which we are using in this circuit. And this is the response of the second order low pass filter, where the gain is 40 dB per decade. Here I can see the gain is 40 dB per decade. So whereas you can observe the slope, that is cutoff frequency fc here, and above that fc it has a pass band, and below that fc it has a stop band. That means it allows only the signals above fc, and it does not allows the signals below fc. So if you observe the low pass and high pass filters, which is constructed by the passive components itself. So if you observe the first order low pass filter, the transfer function h of s is equal to omega c by s plus omega c in case of low pass filter, and whereas in case of high pass filter, s by s plus omega c. So transfer function we can write it as 1 by 1 plus j omega by omega naught, and h of j omega in case of this 1 by 1 minus j omega naught by omega. So in case of second order, so here you can see in case of second order low pass filter, the transfer function will be omega naught square divided by s square plus s into 3 omega naught plus omega naught square. So in case of high pass filter, s square divided by s square plus s into 3 omega naught plus omega naught square. So these are the differences between the first order high pass and low pass filters between when we observe the transfer functions of the filters. So next filter is a band pass filter. So in case of band pass filter, if you observe that it allows only the frequency, here you can observe that ideal response of band pass filter, in which it allows only the frequencies between this FL and FH, frequencies between FL and FH, and it rejects all other frequencies. So this is the ideal response. So the frequencies between this FL and FH will be having the highest gain, that is 1, and the frequencies above this FH is having the gain 0, and frequencies below this FL is having the gain 0. So this band pass filter can be constructed by using low pass and high pass filter. So first we are going to place the high pass filter, which is having the lower cutoff frequency FL, and then after that we are going to place a low pass filter which is having a higher cutoff frequency FH. So if we consider a high pass in series with a low pass, then the response of the filter will be a band pass. Then the response of the filter will be a band pass. So which allows the frequencies between these two levels, that is FH and FL. So the pass band is this, and all other frequencies will be rejected by this band pass filter. So when we are going to consider uh, the practical response of the band pass filter, here you can see FC1, which is decided by the high pass filter, and the FC2, which is decided by the low pass filter, and the maximum gain is going to obtain at F0, is going to obtain at F0. Here you can see, where you can observe. So the signals having the frequencies between these two will be allowed. So here you can observe the blue color section is the pass band. It allows the signals only the frequencies between this FC1 and FC2 and rejects all other frequency components. So band pass filter, here you can see the bandwidth of the band pass filter between, that is bandwidth is given by FC2 minus FC1. So in this band only it is going to allow the signals to pass through it, and the center frequency will be decided by root of FC1 FC2. The center frequency F0 will be given by root of FC1 into FC2, and the quality factor is nothing but the ratio of center frequency to the bandwidth. The quality factor is the ratio of center frequency to the bandwidth of the signal. That is about the band pass filter. And coming to the next one, that is the band stop filter. So when we are going to consider this band stop filter, so within the selected bands, within the selected band, it does not allow the signal to flow through it, and beyond that selected band, it is going to allow the signal frequencies. So here in this ideal response, you can observe that. So the frequencies between FL and FH will not be allowed by this band stop filter. So hence this filter is named as a band stop filter. The selected frequency band, it does not allows the free signals in the selected frequency band and allows all other signals beyond that frequency band. So here it allows the signals, that is the pass band is below FL and above FH, whereas the stop band is going to lie between FL and FH. So this can be constructed by considering a low pass filter. As we have observed, this is the response of a low pass filter, which allows only the low frequency signals, and this is the response of a high pass filter, which allows only the high frequency signals. If we adjust the cutoff frequencies of a low pass and high pass filter, then we can obtain a band stop filter. So when coming to the practical response of the filter, so here you can observe the practical response in a blue line curve. So here the gain is maximum below fc1 and the gain is maximum above fc2. So beyond this, between this fc1 and fc2, the gain will be low. The gain will be low, and at f naught, at center frequency f naught, the gain will be almost very low. The gain will be almost very low. So this is the band stop filter response. So nothing but here the band, what is the difference between band pass filter and band stop filter means, band pass filter allows the frequencies within the selected band, and band stop filter does not allow the frequencies within the selected band. That is only the difference we have observed, you can observe. And coming to the filter response characteristics, according to the pass band appearance, so we can uh, divide the response, we can divide the filters into three types. So here you can see that. So the three types of filters are Butterworth filter, a Bessel filter, and Chebyshev filter. So Butterworth response, which is given in a pink color line. So here you can see, here we are going to consider the low pass filter response, low pass filter response of a Butterworth filter. So Butterworth filter response will be like this. So here you can see it is having the maximum gain, uh, which is having a flat line. You can observe a flat line up to here. So if you are having a cutoff frequency here, so then the attenuation is also very nearer to the cutoff frequency. If you consider the cutoff frequency here, you can see the attenuation is also very nearer. So this is the response of a Butterworth filter. This is how the response of Butterworth filter will be. And coming to Bessel filter, this is the blue line, which is indicated by the blue line. You can see this blue line, as we have observed in the low pass filter section. This resembles the same as the low pass filter response. So the Bessel filter. And coming to Chebyshev filter, it is having a ripples. You can see it is having a ripples in the pass band, and then it is going to attenuate. So this is the Chebyshev filter response. So according to our requirement, we are going to select these three types of filters. We are going to select one of these three types of filters. So what is a Butterworth? So Butterworth filter, which is having a flat pass band and a roll-off rate of minus 20 dB per decade, as we had discussed in our previous section, that is a low-pass filter section. We use this Butterworth filter when all the frequencies in the passband must have the same gain. So next, Chebyshev filter. Coming to the Chebyshev filter, so it is having a ripples in the passband. As we have observed here, you can observe the ripples in the passband. This is called ripples in the passband, and the roll-off rate is greater than minus 20 dB per decade. That is, the attenuation is greater than minus 20 dB per decade. Here you can see the attenuation, and it can be implemented with the fewer poles and less complexity circuit. So the building of this Chebyshev will be requiring a less circuit. And coming to Bessel, linear phase response, ideal for filtering pulse waveforms. So this Bessel is a linear phase response. You can see the response is linear, and this is used for filtering the pulse waveforms. So when we are considering the pulse waveforms, so for filtering those pulse waveforms, in case of some digital modulation techniques, there we are going to use this Bessel filter. And coming to the filter response characteristics, so we are going to discuss here about the damping factor. So the damping factor, uh, which is going to determine the characteristics of that is the response of the filter, that is either it is a Butterworth filter or other another type of filter will be determined by this damping factor. So where you can see here a frequency selective RC circuit, that is nothing but a filter. It may be a low pass filter or it may be a high pass filter, and then it will be given, the signal will be given to this frequency selective network, and also the feedback is provided to this frequency selective network, and then we are giving this to an operational amplifier, so which is going to act as a non-inverting amplifier. So whereas these two resistors, we know that for inverting terminal these two resistors are connected. This is a negative feedback provided by R1, and R2 will be grounded. So the damping factor here is going to depend upon, okay, which is given by 2 minus R1 divided by R2. 2 minus R1 divided by R2. So the output of the signal is fed back to the filter circuit with a negative feedback determined by combination of R1 and R2. So in case of our inverting amplifiers, we have considered there in our applications this as RF and this as R1. So here we are going to consider just this as R1 and R2, nothing, there is no difference, the circuit is same, but here we are going to consider R1 and R2 instead of RF and R1, only the difference is that. So the critical frequency, filter response characteristics you can see. So when we are going to consider the active filters, when we are going to consider the active filters, we are going to consider an operational amplifier, Opamp, so which is going to act as a non-inverting amplifier. Why it is a non-inverting amplifier? Because we are giving input to a positive terminal of operational amplifier. So this input is given to the operational amplifier through a RC network, so which is going to act as a low pass filter, which is going to act as a low pass filter having a single pole. So input is given to a low pass filter circuit, then the output of this low pass filter circuit is only the lower frequencies. That frequency signals will be amplified by this operational amplifier, which is going to act as a non-inverting amplifier. So here, so the FC will be, that is the cutoff frequency, will be decided by this RC component, as we have seen in the last sections. So we are going to use the same FC for low pass as well as high pass circuit also. If we consider the roll-off rate, so here you can see the three stages, that is what we have discussed in the low pass filter as well as high pass filter passive networks, that is first order, second order, third order. So as we have observed here, three RC circuits, so RC, RC and RC, and three operational amplifiers. This is a single RC circuit operational amplifier, that is either it may be a low pass or it may be high pass, that depends upon the arrangement of this RC circuit. So if it is a low pass circuit, then you can see here three Opamp circuits. So it is called as third order uh, third order filter, in which if you use low pass, then it is called as third order low pass filter, and if you use high pass, then it is called as uh, third order high pass filter. So if we use RC circuits here, two RC circuits, if you use in the place of RC circuits, if you are using a second order low pass RC circuit, then it becomes a second order low pass RC and it also becomes a second order low pass RC, and it also becomes a second order low pass RC. 2 and 2 and 2 will become a higher order low pass filter. So as we are going to increase the number of orders, then what is going to happen in our response of the filter, that is the roll off rate is going to increase. So here, as we are going to consider a single RC circuit, the roll-off rate will be minus 20 dB per decade for each RC circuit, for each circuit, and then minus 20 dB, minus 20 dB, minus 20 dB, which becomes minus 60 dB per decade. So the total roll-off rate of this circuit response will be minus 60 dB per decade. That means the line which we have considered the line in the stop band, the line in the stop band is going towards the cutoff frequency, is going towards the cutoff frequency that we have observed here. So here you can observe the response, actual response, by considering only RC circuit. So as we are going to increase number of orders, that is this is the first order, and this is the response of second order, and this is the response of third order. So if you use a fourth order, fifth order, then this slope will be going to move towards this FC. So when we are going to come close towards this FC, then we can say that uh, it is going to produce, our filter is going to produce the response which is similar to the ideal response of the filter, which is similar to the ideal response of the filter. So here the roll off depends upon number of poles, that is nothing but number of circuits we are introducing, the number of RC circuits we are introducing in the filter response. So this is the topic we have discussed today. Thank you. And in the next class, we are going to discuss about active filters, active high pass and active low pass filters, and their response we are going to observe in the next class. Thank you, students.